Okay, this first question is talking about both a single slit, which is this expression here, and a double slit combination. So why is there zero intensity observed at position A? You have to bring in that there's a combined effect of the single slit diffraction pattern and the double slit interference for the first mark. Some recognition that there is a minimum caused by the single slit pattern, which helps to explain how the double slit gets cancelled out. This comes in the more complex description here, that the missing maxima of the double slit at A are cancelled because of the single slit waves meeting the double slit pattern. So it's a very complex situation, in fact, a bit more difficult than you might expect. Okay, the second part could be misleading because it gives you the idea that this is a double slit question and you have to use S equals lambda D over D, which is a double slit expression. If you do that, you get no marks at all. It is in fact a single slit situation. The clue is in the width of each slit. It is pointing towards using theta equals lambda over B, not S equals lambda D over D. So you can work out theta, the angle that's going from here to just about the first place over there. In general terms, you can make it theta equals lambda over B, and that will be in radians. You also know that the distance is 7 meters and a very small distance there as well, so you can set up a short angle of theta as well using small angle approximation there. So you've got theta, those two thetas are the same, so make the two the same like this. You know what lambda is, so B can be easily found by putting lambda in and giving you an answer of 1.0 times 10 to the minus 4 meters. Now part 3 actually is a double slit separation question. They want to know what the separation of two slits is. You will be using S equals lambda D over D. The problem is you're looking at it thinking, well, what actually is the value for 3 fringes? I can't see a third fringe. That third fringe has been taken away, not the central maximum here, but it's been taken away by the single slit interference that's taken place, a cancelling that took place earlier on. So in fact, that actually is where the next double slit fringe would be, and that means you can go you can do the 3 fringes and use a value of 4.1 times 10 to the minus 2 meters. As soon as you put that length then into S equals lambda D over D, you'll get the answer 3 times 10 to the minus 4 meters there. Okay, now the diffraction grating, as we placed a double slit, so the diffraction grating 600 lines per millimeter. Differences that you might see, state them, also explain the differences as well. Fringes further apart, because you've got much lower slit separations. You've got 600 lines per millimeter now, and that's from S equals lambda D over D. The fringes are narrower and sharper because there'll be a region for constructive interference which will be much smaller now because you've got more slits. Also, because you've got more slits per millimeter, you'll have a higher intensity for the peaks, and that's since more light can pass through the diffraction grate. The final question requires you to use this lesser used expression, which is in the topic 9 booklet. Look for it there. And in fact, you're going to use these 2 parts of it here rather than resolvents. So you're going to rearrange it to give you n equals lambda m delta lambda, and you can now find those bits of information from what you've been given. So your delta lambda is the difference between the 2 wavelengths that you've been given. So it's this value here. Show that and you get a mark. We arrange this expression here until you get n equals lambda over m delta lambda. N is the number of lines illuminated. You're going to need to use that. M is the order of the diffraction line you're seeing, the one that you see through the diffraction grating, and that's 2. It's been given in the question here. It says that the second order spectrum has been seen. Put your values in, 589. I haven't bothered with nanometers because it'll cancel out with this. That's nanometers. It can be just 589 and 0.597. And you eventually will find that 493 lines are illuminated. Now, you're told that 600 lines are per millimeter on the diffraction grating, you've got 493 parts of 600, therefore 0.82 millimeters is the beam width.